So we've seen so far how to work with a single random variable when it's continuous or discrete, but now we need to worry about the case of multiple random variables. And for the most part, we're going to be interested in continuous random variables, okay? So if we have two random variables, x and y, well, we have to be able to describe their distribution. And we do that by using this thing called a joint probability density function. Okay, so this maps the R2 basically into the non-negative reals. And it has this property that when we integrate it in the plane, we get 1. Okay? Very often we're interested in marginal PDFs. In other words, we want to know basically what happens when we integrate, say, y out, and then we get just the PDF of x. Or what happens when we integrate x out, we get the PDF of y. Okay? And we're going to see why. There's an actual application of that. Well, the joint CDF is really nothing more than the probability that capital X is less than or equal to small x, capital Y is less than or equal to small y. And of course, whenever we want the probability that we're in a certain area, we just integrate over that area. That gives us a CDF. And the joint CDF and PDF have that same sort of derivative relationship like we saw before, except now since we have two variables, we have to take a partial derivative with respect to x and y. Okay? Independence is actually really important with multiple random variables, and we're going to say that x and y are independent. And again, there's a lot of different definitions of this. But remember I said earlier that I'd give you a different definition, and the reason why is this is really what we do when we have multiple random variables, okay? So we're going to say they're independent if the joint PDF factors as a product of their marginals, okay? And a consequence of that is that the CDF also factors, all right? Now, one thing that we're interested in is we're interested often in conditional PDFs. In other words, if we freeze the value, say, of y, what is the PDF of x? It's like looking at a cross-section in a sense, right? And it turns out this is how we define the conditional PDF of x with respect to y. We just take the joint PDF and it's divided by the marginal with respect to y. And we can get the conditional PDF of y with respect to x in a similar way. Now there's two reasons why we're interested in getting that conditional PDF. The first is that we have a nice condition for independence. Basically, if the conditional PDFs are the same as the marginals for all x and y, then it's independent. X and y are independent. We can also find conditional expectations. If we take the conditional PDF and integrate it over that random variable, we get the expectation of x given capital Y is equal to y. So this is something that we're interested in doing sometimes. Now there's two last things that we're interested in. The first is a variable transformation. And so we actually did this when we were looking at calculus before, okay? Suppose we have n random variables, we know they're joint PDF, but now we want to transform it to some new n random variables. And we want to know what is the joint PDF for the y's, okay? So we have in our mind this notion that yi is some function of all the x's, okay? But in order to be able to make this variable transformation, it has to be the case that this relationship is invertible. In other words, I have to be able to solve for the x's in terms of the y's. This is basically the same as the condition that this mapping is 1-to-1. Okay, from this vector to this vector, it's a 1-to-1 mapping. And it turns out that if this is the case, then I can get the PDF. Basically, all I do is I substitute in, I take my old joint PDF, I substitute in for each of the functions, each of the random variables in terms of y, and I multiply it by the absolute value of the Jacobian. Okay, so this is partial of h1 with respect to y1, okay, partial of h1 with respect to y2, partial of h1 all the way down with respect to y1. And notice that each row I'm taking the ith row, I'm taking the partial of hi, and in the column it's with respect to yj for the jth column. And this gives us the transformation, okay? And we'll do some problems practicing that. Okay, let's look at covariance and correlation next. So let's suppose, for example, we have two random variables x and y. This is how we define their covariance. And you can show that this reduces down to the following. Just like the variance reduced down, the covariance reduces down. And you can see if x was equal to y, this would actually be the expression for the variance. Why do we care about the covariance? Well, we need it to calculate the correlation. So the correlation between x and y, which we normally denote by rho, is the covariance which is scaled by, and this should actually be the standard deviation for each of the variables. That's x and y. Sorry about that. Okay. And what the covariance measures, I mean the correlation measures, and it often is kind of misunderstood, it actually measures the strength of the linear relationship between x and y. Notice that word linear, that's very important. So this is why we use correlation coefficients in linear regression, right? We want the strength of the linear relation. But if there's a quadratic relation, okay, or a cubic relation, it might not show much of a correlation. In fact, if it's a cubic or quadratic, there might be zero correlation, okay? Now the correlation is always between -1 and 1. You can prove that. If rho is positive, we say it's a positive correlation. If rho is negative, it's called a negative correlation. And what that means is that as x increases, if you have a positive correlation, it means that as x increases, y tends to increase also on average. Negative means that if x increases, y tends to decrease. So we could think of lots of things that have positive and negative correlations, right? The more you study, the higher your grade is, positive correlation. The more you exercise, the less your weight is, negative correlation. Now, the last thing we want to mention is this notion of correlation and independence. And this is something that people often get confused about. If two random variables are independent, their correlation is 0. But the converse is not true. Just because the correlation is 0 does not mean that x and y are independent. And I'll give you an example in the homework that shows this, okay? Okay, this is pretty much all the basics we need to know of probability theory. And we're going to come back and work some homework problems to kind of flesh out a lot of these concepts.